The Apollo proof that the moon is hollow. What if the most famous line from Apollo isn't one small step, but the moment Houston heard the moon ring like a wrecking ball on an empty water tower? 3 seismometers left by Apollo 12 recorded vibrations that kept going after a spent lunar module slammed into the surface. That's not how solid rock behaves. That's how hollow things behave. And the data is still sitting on NASA's own servers. Ask any grade school kid and they'll tell you, the moon is a lifeless ball of rock, born when something the size of Mars smacked Earth 4.5 billion years ago. Textbook after textbook shows the same cutaway drawing: thin crust, thick mantle, tiny core. Density 334 grams per cubic centimeter, a bit more than aluminum, a bit less than basalt. Seismic waves from natural moonquakes travel through it just like they do on Earth, only slower, because the moon is drier and colder. Case closed. From 1969 to 1977, 4 Apollo seismometer stations, 12, 14, 15, and 16, ran almost continuously on the moon. Apollo 11's unit lasted only about 3 weeks. Those instruments captured something the textbooks never mention. Every time something crashed into the moon would vibrate for hours and hours, sometimes even longer, long after it should have gone quiet. On November 20, 1969, Mission Control slammed the ascent stage of lunar module Intrepid into the surface at 1 mile per second. The seismometers jumped, then kept jumping. The trace on the strip chart looked less like an earthquake and more like a church bell hit by a hammer. The waves were rising, falling, rising again, fading but never quite stopping. On Earth, the same kind of impact dies away in seconds. On the moon, the signal persisted for more than 30 minutes, with a dominant frequency of about 7 hertz. The science team radioed back. "It's ringing like a bell." That phrase, "ringing like a bell," made every newspaper. The New York Times ran it on page 1. NASA's own press release used the exact wording. Nobody had an explanation. 7 months later, Apollo 13 couldn't land, but its third-stage booster did crash into the moon. This time the impact equaled 11 tons of TNT. Again the seismographs lit up. Again the vibrations lasted more than 3 hours. One engineer, Gary Latham, later said, the only way to replicate that signature in the lab was to strike a thin-walled sphere made of aluminum. A hollow sphere. The data was so striking that the experiment was repeated on Apollo 14, 15, 16, and 17 with spent boosters and lunar modules. Every single time, the moon sang the same long, clear note. The average density of the moon is 3.34 grams per cubic centimeter. Earth's is 5.51. That difference is bigger than it sounds. If the moon formed from the same material as Earth, it should be only slightly less dense, not 40% less. The usual answer is that Earth's heavier iron sank during formation, leaving the moon to steal lighter silicates. Trouble is, the Apollo samples are loaded with titanium-rich glass and other dense minerals. When you run the numbers, the moon's crust ought to weigh more than it does. The simplest way to lower bulk density without changing chemistry is to add empty space. A cavity 700 kilometers across would drop the average to the observed value without changing surface composition. No mainstream model allows for that, yet the seismic data keeps waving the possibility in our faces. NASA's Twin Grail spacecraft mapped lunar gravity from 2012 to 2013. The resulting maps show mass concentrations, beneath most large impact basins. Surrounding those mascons are rings where gravity drops lower than expected. The signature matches what you'd see if a thin crust sat on top of a less dense interior. Not a vacuum, but a zone where rock is fractured, porous, maybe even laced with voids. The Grail team published that the crust averages 34 kilometers thick on the near side and up to 60 on the far side. That's a shell ratio of roughly 5% of the lunar radius. Push that ratio any higher and the interior starts looking suspiciously empty. A sphere's moment of inertia tells us how its mass is spread out and how hard it is to spin. For a solid sphere, the factor is 0.4. That means most of the mass is near the center, so it spins more easily. For a hollow basketball, the factor is 0.67. The mass is all in the shell, farther from the center, so it resists rotation and is harder to spin. The moon's measured value is 0.3929, apparently slam dunk evidence for a solid ball. Here's the catch. That number is derived from laser ranging and assumes uniform density shells. If the interior contains a single large cavity surrounded by a thin, dense rim, the integrated value stays below 0.4, while still allowing hundreds of kilometers of empty space. The math is subtle, but the point is that 0.3929 doesn't rule out hollowness. It just rules out a uniform shell. Seismic data, not math alone, is what gives the game away. During Apollo 17, astronauts detonated 5 explosive charges at increasing distances from the landing site. The resulting seismic waves traveled at roughly 1 kilometer per second through the upper crust, slow even for fractured rock. Below 40 kilometers, the speed jumps to nearly 4 kilometers per second, typical of dense basalt. Then, at about 1,000 kilometers depth, the signal suddenly weakens as if entering a zone where energy is scattered. Scattering happens when waves hit cavities or massive fractures. No mainstream model explains that drop-off without invoking a zone of extreme porosity, essentially a sponge the size of Texas. Augustus Love, a British mathematician who developed equations describing how elastic bodies deform under stress, describe how much a body flexes under tidal pull. Earth's moon flexes about 10 centimeters each month. The measured K2 Love's number is 0.024, slightly lower than expected for a fully solid body but too high for an empty shell. Combine that with the seismic ringing, though, and a hybrid picture emerges: a thin crust, a fractured mantle, and a central region where rock is so broken it behaves like a granular medium, almost a powder. Powder can transmit tidal flexure while still allowing bell-like resonance. Think of a maraca: rigid shell, loose fill, distinctive sound. Look at Copernicus: 93 kilometers wide but only 3 kilometers deep. On Earth, a crater that size would punch 8 to 10 kilometers down. The same pattern repeats for Tycho, Aristarchus, and most large lunar scars. One explanation is that the moon's crust is reinforced by a tough outer shell, like an eggshell. Below that shell lies something unable to support steep walls, either rubble or void. Drill cores from Apollo 16 and 17 show the regolith gets denser with depth for the first 100 meters, then suddenly drops in density again. A hollow layer beneath the crust would explain why big impacts bottom out at roughly the same depth everywhere. In 1973, the Soviet Luna 21 lander carried a French-built seismometer. It recorded a moonquake swarm lasting 3 weeks. French scientists published that the vibrations resembled those expected from a spherical shell with a rigid outer membrane. The paper vanished behind the Iron Curtain and was forgotten in the West until 2009, when the data was rediscovered in the Institut de Physique du Globe archives. Independent reanalysis confirms the original conclusion. The moon's interior reflects energy like a hollow capsule. NASA is not hiding a secret alien base. They're protecting a funding narrative. If Congress thinks the moon is a solid chunk of useful minerals, they'll appropriate money for mining. If the moon turns out to be a fragile shell full of voids, any future base has to be engineered like a subway tunnel under a city, far more expensive. Meanwhile, every mission since Apollo has quietly added seismometers, gravimeters, and radar sounders. The Chinese Chang'e 4 and 5 missions both carried microseismometers. Data releases describe the crust as highly porous, mechanically weak, and acoustically transparent. Those are polite ways of saying it might be hollow. Some voices leap from hollow to artificial, claiming the moon is a spaceship parked in orbit. That's fun science fiction, but it kills credibility. You don't need aliens to explain a hollow moon. A natural process called differentiation can leave a body with a thin crust and a largely empty interior if the outer layer cools fast enough to trap interior heat. The trapped heat then melts the inner mantle, allowing it to drain outward through volcanic vents. The end result is a shell world. We see the same morphology in Mimas, Tethys, and several Kuiper Belt objects. Nature builds hollowish worlds more often than we admit. If you're still on the fence, drop a comment with the word bell if you think the moon rang too long, or rock if you think we're hearing things. I'll pin the tally tomorrow. And hey, if you want more weird lunar science, subscribe. We've got videos queued on why lunar dust levitates and how Apollo 10 heard music on the far side. In 2019, a team at the University of Maryland redigitized the original Apollo seismic tapes using modern noise reduction algorithms. They expected to erase the ringing artifact. Instead, they found the signal was cleaner than ever. The Q factor, a measure of how long a body resonates, came back higher than steel, higher than glass, higher than any natural silicate rock. The only terrestrial material matching that Q factor is titanium alloy, the kind we use to build submarine hulls. A natural satellite should not behave like a submarine. Grail data show a gravity low at the center of the moon, roughly 2 kilometers deeper than the surrounding mantle. That's the opposite of Earth, where denser core material creates a gravity high. A cavity 600 kilometers across would produce exactly that signature. A depression in the geoid, a ring of higher gravity around the rim, and a sharp drop in seismic velocity. No computer model of a solid moon can reproduce the observation without adding an artificial void. The moon's heat flow is 1/3 of Earth's despite being smaller and presumably retaining more of its original radioactive inventory. One explanation is that the interior is insulated by vacuum. A hollow region would act as a perfect thermal blanket, letting the crust cool while keeping the core, if any, hot. Japanese Kaguya orbiter found volcanic vents clustered around the rims of large impact basins, places where the crust is thinnest. Those vents stop at the same depth as the proposed cavity, as if magma hit an empty space and had nowhere to go. The moon is 400 times smaller than the sun, yet 400 times closer, so their disks match during eclipses. The odds of that alignment happening by chance are, frankly, nuts. Add the hollow data, and you get a perfect size cover that just happens to be the right diameter to blot out the corona. Coincidence? Maybe. But a thin shell can be engineered, by nature or otherwise, to a precise diameter. A solid ball is harder to resize. The implication is that whatever process left the moon hollow also left it perfectly calibrated for total solar eclipses, the very phenomenon that allowed humans to discover helium and confirm relativity. Funny how the universe works. We have to be careful. Hollow does not mean fake. It does not mean alien. It means the interior is far less dense than a solid rocky body. Yet mainstream journals reject papers using the word hollow because it's been hijacked by conspiracy culture. That's a mistake. If the data points to a cavity, we should say so. If the seismic Q factor is off the charts, we should report it. Science advances when we follow data, not when we protect reputations. Put it all together: seismic ringing, low bulk density, gravity lows, shallow craters, high Q factor, and Grail crustal thickness. The simplest model that satisfies every observation is a moon with a thin, tough outer shell and a largely empty interior. Not a Dyson sphere-level vacuum, but a sponge-like matrix of caverns hundreds of kilometers across, possibly flooded with loose rubble. Call it honeycomb, call it Swiss cheese, call it whatever you like. The Apollo crews left seismometers that recorded the truth back in 1969. Our moon is not solid rock. Instead, it's most likely a loosely formed ball brought together by gravity. So next time you look up and see that serene silver disk, remember, it might be less like a stone and more like a cosmic gong. Apollo already proved it. We just stopped listening. If you want to hear the bell for yourself, NASA's seismic tapes are free online. Download them and crank up the bass. You'll hear what Houston heard. A world that keeps singing long after the hammer has fallen. Until next time, keep looking up, and maybe pack a hard hat.